Okay, welcome to this video. We want to prove the cauchy Bunyakowsky Schwarz inequality. What this inequality says? It says that if we have this is a semi-inner product on H, then the absolute value of in a semi-inner product between x and y squared less than or equal the semi-inner product between x and x times the semi-inner product between y and y for all x and y in H. What's H? H is a vector space over F. F here is like the real field and the complex field. Okay, let's start our proof. We will start our proof if we have alpha belongs to F. Okay, alpha belongs to F and x and y belongs to H. Then we know from the semi-inner product definition that it's always the semi-inner product is always more than or equal 0. So let's take the semi-inner product between x minus alpha y with itself, x minus alpha y. Okay, what's this equal? It's equal semi-inner product between x and x minus alpha semi-inner product between y and x minus the conjugate of alpha, okay, semi-inner product between x and y plus alpha squared, the absolute value of alpha squared, the semi-inner product between y and y. Okay, let's suppose that the semi-inner product between y and x is equal b times e to the power I theta. Here b is more than or equal 0. Okay, and let alpha is equal e to the minus I theta, okay, times t. Here t in real number. Okay, what's this inequality becomes 0 less than or equal the inner product between x and x, the minus e to the minus I theta t, right? B to the b times e to the power I theta, okay, minus e to the I theta power times t, b times e to the power I theta minus I theta plus t squared, the inner product between y and y. Okay, what this becomes, let's cancel this with this and this with this, so it comes like the semi-inner product between x and x minus 2 bt, right, plus t squared semi-inner product between y and y. Okay, here actually let's take like we know this is constant and this is constant, so let's replace those with like a let's replace this with like the semi-inner product between x and x. Let's put it c. Okay, c minus 2b t times b plus let's take this a. Okay, a t squared, a times t squared. So here suppose this is a and this is c. Okay, now let's suppose that this one is q of t, or this is quadratic polynomials. This is quadratic polynomials. It's like this: a t squared minus 2 bt plus c. So this is q of t, and this one is more than or equal 0. So we know that this quadratic polynomial in a real in the real variables t, and this one is more than or equal 0. So this implies that this equation, if q of t is equal 0, then we have at most one real solution, right? Solution t. But if we have q of t more than 0, okay, then what we have is like from this quadratic polynomials or formula, from the quadratic formula, we know that the discriminant is not positive. So we have 0 is more than or equal the discriminant. Discriminant is like 4. We put 4b squared, okay, minus 4 ac, 4b squared, because we have here minus 2 minus 2, it's 4, so b squared, okay, minus 2 squared, it's b squared, sorry, it's b squared, so minus 2b, it's squared, it's 4b squared minus 4ac. It implies that 4b squared more than or equal 4ac, and it implies that b squared more than or equal ac. Okay, let's take another page here. Okay, what's b squared? B squared, actually b squared, we can take it from here, okay, b squared is from here. So the let's take the absolute to the both side. So absolute for the semi-inner product between y and x equal absolute b times e to the I theta. But what's this? This equal to b. So let's take the square for both sides. So b squared is equal the absolute value for inner product between y and x all squared. But this actually same like the absolute value of x, of inner product between x and y squared. Okay, now I think everything is clear. So b squared here is the absolute value of inner product between x and y squared more than or equal a. What's a? A here is inner product between y and y. And what's c? C is the inner product between x and x. So we have done our proof.